Thanks again, Thomas, for agreeing to give a talk about your work on marine heat waves. I always see you commenting on things, usually very astutely on Twitter and the like. Maybe you're on Blue Sky now, I don't quite recall. Um, but yeah, Thomas is at the University of Bern, and he focuses on marine heat waves and compound interactions. And he will talk about some of those, including the biogeochemical aspects, in today's talk. So thanks again, Thomas, for 20 or so minutes. The floor is yours.
Yeah, thanks, Colin, for the introduction. Nice introduction, also for the invitation to give the talk. So let's try to share my screen. Does that work? Should
That looks
Okay.
perfect. Yeah.
Okay. So yeah, so I'm gonna talk a little bit about the compound marine heat waves and biogeochemical extremes, a bit about the drivers, changes, and impacts. So before I do that, just a quick reminder why we actually care about the ocean. So I saw that many talks in that webinar were more on the land side and atmospheric science side. So, but we also care about the ocean because the ocean takes up about 90% of the excess heat. It takes up about 20 or to 30% of the anthropogenic carbon we emit into the atmosphere due to the burning of fossil fuel and land use change. But obviously, it also provides food and other services to more than 3 billion people on Earth, and the vast majority of them actually and living in developing countries. So it's a really important player in the climate system, but overall also for the human system. But the ocean is currently under stress, so it's getting warmer because of the uptake of excess heat. So about by zero point 0.9 at the sea surface, zero point 0.9 degrees over the last 150 years, and is continued to do so in the future, depending on the future scenario, a little bit more or a little bit less. So the uptake of anthropogenic carbon also leads to a decrease in pH, so basically an increase in the hydrogen ion concentration due to the uptake of CO2, which dissociates with water, forming carbonic acid, which is really short-lived, and then actually forms bicarbonate. And through these reactions, actually hydrogen ion concentration is increasing, and therefore the pH is decreasing. And we know that actually the pH has decreased by about zero point 0.1 units over the last 150 years, and it's continued to do so due to the increase in atmospheric CO2. And also the oxygen is actually decreasing by about 1 to 3% over the last 60 years, mainly because gases are less soluble in warmer waters. So that's one of the effects. But over the main effect is because the ocean gets more stratified. So the mixing and the ventilation is decreased. And if the ventilation decreases, then actually also the ocean circulation bring less oxygen-rich surface water to the deeper ocean. So the consumption is still going on by bacteria of oxygen, but it's not really replaced anymore, the low oxygen water with rich oxygen water because the ventilation is actually decreasing. And that actually leads to ocean deoxygenation. And we know that now for a long time, but we have somehow realized that over the last few years to decades, that these changes are not happening gradually. They are punctuated by extreme events. For example, this marine heat wave in the Mediterranean Sea was really severe in 2022, with actually sea surface temperatures 5 degrees higher than normal, which is actually quite enormous when we think that actually ocean temperature variability is usually quite damped compared to atmospheric temperature variability. So, and so we made a compilation a few years ago about where were actually the most impactful marine heat waves in the ocean. So where we know that they had impacts, because often we do not know and we do not have the observational system to say that sea surface temperature anomalies or temperature anomalies in general have an impact on ecosystems. But here we actually know the literature. And so in the Mediterranean Sea, there was a huge marine heat wave in 2003, but also in Northwest Atlantic, in the Gulf of Alaska, and then we had this huge blob in 2013 to 2015, and we had several marine heat waves which had huge impacts on warm water corals actually around Australia in many years over the last 20 years. So they can have huge impacts. And why do we actually care about them? Before I come to the ecosystem impacts, they can also actually impact weather system, for example, but they can also impact the CO2 uptake by the ocean. And we just had a recent paper, which is now in press, where we looked actually at the impact of all marine heat waves over the last 30 years. What were the impact on actually air-sea CO2 exchange? And here on the top left, you see a composite of all marine heat waves, how they actually alter the CO2 uptake or release by the ocean. And if it's red, that means actually the sea air CO2 flux anomaly is positive, so less uptake. And if it's blue, it means more uptake. So you see that actually in the subtropics. So when we go here to the low to mid northern hemisphere latitudes, actually we usually have an uptake of carbon by the ocean, but during marine heat waves, that carbon uptake is actually reduced, significantly reduced. Whereas, for example, in the eastern equatorial Pacific, where we usually have an outgassing of carbon because we have upwelling of carbon-rich deep water to the surface, this upwelling and therefore also the carbon exchange with the atmosphere is actually reduced. So we have anomalous uptake of carbon during marine heat waves and in this region. And if we do the math then, and if we look at globally and we do aggregate all these heat waves together and the CO2 flux anomalies, we see that during marine heat waves of the last 30 years, the global ocean CO2 uptake dropped by about 8%, but it can actually drop by about 30% depending on the region. So in the low to mid latitude, as I said, reduced uptake during heat waves. In the tropical Pacific and high latitudes, reduced outgassing. So that means overall, at least in our analysis, about 50% of the ocean surface area, the CO2 flux is significantly weakened. So that means if we have outgassing, that is weakened, so we have anomalous uptake. If we have uptake, this uptake is weakened and we have anomalous outgassing. Why is that so? So we then actually looked at the drivers of this. So the CO2 flux into the ocean is basically the difference proportional to the difference between the PCO2 in the ocean minus the PCO2 in the atmosphere times the solubility times the gas exchange rate, which is depending on the wind strength. And when we look at the main driving factor of the air CO2 flux anomalies during marine heat waves, we clearly see it's this term here. So that basically the PCO2 in the ocean, which drives most of the anomaly. And then we decompose that term into a contribution of carbon, so DAC, a contribution of alkalinity, basically the buffering factor of the seawater, a contribution of temperature, and the contribution of salinity, which can also drive or change the PCO2 in the ocean. And if we do that, then we see that in the low to mid latitudes is mainly just the temperature effect, which increases the PCO2. So when we have a marine heat wave, the temperature increases, that increases the PCO2 in the ocean and therefore decreases actually the uptake. Whereas in the equatorial Pacific here, for example, it's mainly the carbon which changes the PCO2. So because of often reduced upwelling during marine heat waves, the DAC is reduced and therefore the PCO2 in the ocean is also reduced, and then we have an anomalous uptake. So we did this composition, and it's mainly the temperature which dominates in the low to mid latitudes, whereas the carbon itself in the ocean, which dominates actually in the equatorial Pacific, but also in the high latitudes. So that's the impact on the air sea CO2 flux. But most of the people, when we talk about marine heat wave, are concerned about the ecological impacts. And I think really this paper by Tom Wernberg was really an eye-opener because they actually investigated the impact of the Western Australian marine heat wave on the ecosystem here in the eastern part of Australia. or of the sea actually, or of the western part of Australia. And what they see is actually that this ecosystem is usually dominated by kelp forests. So about 90% of the ecosystem or of the reef cover is dominated or is actually kelp forest. And then the heat wave hit that coast in 2000, end of 2010. So here, and the whole ecosystem structure just changed. So kelp forests were not abundant anymore, and seaweed turf took over. So there was a total flip in the ecosystem structure from one year to the other due to this heat wave. And yeah, that was really an eye opener. And then there were many actually studies looked at the impact of heat waves on ecosystems. We know that warm water corals, kelp forests, as shown here, are really sensitive to warm waters and to these events. But we also look then at fisheries. So do the fish also somehow or change, for example, the biomass or the location when a heat wave actually hits a certain region? And here we actually, or colleagues from the US, so Alexa Fredstone and Malin Pinsky and William Chung and colleagues, they analyzed about 250 sea bottom heat waves from 1993 to 2019. So they used about 80,000 holes from a long-term survey of North Atlantic, Pacific, and European continental shelf ecosystems. And what you see here is basically the biomass log ratio. So that means how the biomass changes from one year to the other. And on the x-axis, you see the marine heat wave cumulative intensity. So it's basically the strength of the heat wave. And what they actually found is that marine heat waves were not associated with a decline in fish biomass. So this distribution here, the red one here, is the fish biomass distribution during marine heat waves, and the blue one during non-marine heat wave years. So they couldn't say that there is actually a really significant impact. And that somehow puzzled a little bit the community. So should we actually rethink the effect of marine heat waves on fish, or what is actually the cause of that? Of course, this data set has its own weaknesses, but maybe there are other drivers which can actually drive low fish biomass events. So then my former PhD student, Natasha Löckri, she coupled a fully coupled Earth system model to a fish model. So it was actually, so she had this GFDL ESM2M, she coupled it with a DBM, that's a global fish model, and then she looked in the model what causes actually low fish biomass event. So instead of looking at the hazard first, she looked at the impact first, and then she went back and looked what were actually the conditions during these low fish biomass events in the model. And what she actually found is that first, the most influential driver of low fish biomass is actually not temperature, it was low net primary productivity, but more importantly, she actually showed that compound events are a necessary condition for extremely low fish biomass over about 80% of the global ocean. So it's really the combination of drivers which leads to low fish biomass events, at least in that model. And if we go back then to these big heat waves I've shown you at the beginning, and this is the blob, and we run a regional biogeochemical physical model, ocean model, in that region from about 90 to about 2017. So the ETH group led by Nikki Gruber did that. And we looked actually at the biogeochemical conditions during the blob. So we always talked about heat and really high temperatures during the blob, but what were actually the associated biogeochemical conditions? And if we look at the blob here, we have seen that it was not only actually heat wave, so often we also have low oxygen conditions, so if it's actually orange. We also had often high acidity conditions when we have this purple color here, so that's basically the area affected in that box. And then often we actually had triple compound extremes, so all these three stressors were extreme at the same time. So probably the big impacts we have seen during the blob were not only driven by the extreme heat, maybe they were also driven by the high acidity levels and low oxygen levels. So underscoring again that probably heat waves are not always coming alone. They are actually associated with other extreme events, so compound extremes. And if we look at the conditions, so on the left here, on the chlorophyll conditions during marine heat waves for these most impactful marine heat waves I've shown you at the beginning, here in the middle at the H plus anomalies during marine heat waves. So that means H plus anomalies. So here we actually show the percentile of the H plus anomalies during that marine heat wave in the overall distribution. These H plus anomalies usually actually have. So for example, here in the Eastern Equatorial Pacific, if we have a really low percentile, that means H plus anomalies were really extremely low, and usually actually H plus anomalies are higher than this because they actually fall here actually in the tenth or even the fifth percentile of the normal H plus anomaly distribution. And what we see is actually during marine heat waves, when we then combine everything and look, where do we have marine heat wave and low chlorophyll events, marine heat wave and high acidity events, and marine heat wave and high acidity and low chlorophyll events, that actually most of these most impactful marine heat waves also had some biogeochemical extremes associated with it. So at the same time and same space. So for example, here in the Eastern Equatorial Pacific, the marine heat wave was associated also with low chlorophyll events. And here around actually Australia, a lot of marine heat waves were associated also with high acidity extremes and or even were triple compound extremes. So when we then look only at marine heat waves and low net primary production events, so if the chlorophyll concentration, for example, is really low or the primary production is actually really low, where do these low extreme primary production events co-occur with heat waves? And that's shown on that map. So that's based on satellite-based observations. And we basically show here the likelihood multiplication factor. So if it's above 1, that means the compound event frequency is higher than we would expect just from the probability we would expect from the univariate frequency. So we defined here the extreme events with the 90th percentile for marine heat waves and the 10th percentile for NPP. So we would expect just by chance that these compound events would occur every 100th day, but they actually occur in the Eastern Equatorial Pacific and in the Mid-Pacific actually twice as likely than we would expect just by chance. In the high latitudes, they almost never actually occur, and also in the Southern Ocean and around Antarctica. Here, actually, the satellite data is not so robust and clear, so I would not put too much emphasis here around Antarctica. And then we looked at in the models what are actually the driving factors of these compound events. And we only have in the models, we use two different models, and here is shown only one. And actually, they really show different drivers in the high latitudes, but similar drivers in the low latitudes. So that's why I'm only showing here the low latitudes, so the low to mid latitudes. So what happens during marine heat waves, we have low phytoplankton production. So especially the small phytoplankton decrease the most, whereas large phytoplankton also decreases a little bit. So there's a shift in the relative distribution of the small to large phytoplankton. And what is driving that shift? So temperature is actually good for the phytoplankton production. They like that the organisms. But the nutrient concentration, so the nutrient limitation decreases the NPP. So we have less nutrients usually during marine heat waves in these regions because we increase heat waves increase the stratification, and therefore the nutrients concentration is lower. And then at the same time, also the biomass is actually decreased because the phytoplankton loss exceeds, so it's actually increased due to the grazing, which is increased during higher temperatures. So that's for the low to mid latitudes. In the high latitudes, unfortunately, we couldn't say anything about the drivers because the models were really different. And that also shows that the models are not really yet really capable of confidentially simulate those compound events in the high latitudes. However, so when we look then at heat wave and high acidity extremes, so that's a different kind of compound event. That's again based on observational based data. And if it's red, that means more frequent compound events, and blue, less frequent compound events than we would expect just by chance. And what we see here again, so it's mostly in the low to mid latitudes where these marine heat wave high acidity extremes co-occur. And in the eastern equatorial Pacific, they actually occur almost never together. And in the Southern Ocean, also not. When it comes to carbon, these data sets, the global data sets, have a lot of uncertainties because we do not have a lot of PCO2 measurements in the ocean. So you have to interpolate and extrapolate the data heavily. So that's why we actually put also station-based time series data here on that figure and then calculated basically the compound event frequency just based on one single location here and here and here. And if they have the same color as the underlying actually map, that means that our reconstruction of the underlying map actually matches quite well the time series station-based data. And it actually matches relatively well. Here in the eastern equatorial Pacific, the same color, and in the low to mid latitudes, almost also reddish color. So that means higher frequency of these events. Why is that so? So mathematically, it's impossible to decompose actually the LMF into its drivers. So that's why we look here at the correlation coefficient of temperature and H plus. And that pattern here on the left looks almost similar to that pattern here. So we have actually quite a high confidence that we can actually explain just by the correlation coefficients actually the pattern of these compound extreme events. And then we can mathematically decompose that into a contribution from temperature and contribution of DAC, so carbon. And usually during these compound extremes, actually the temperature boosts the likelihood of these compound extremes, whereas the carbon always dampens the likelihood. And it's the regional balance between these two effects which leads then to the overall pattern we see here on the left side. So to make it a bit simple, so in the eastern equatorial Pacific, when we have a heat wave, that actually inhibits then the upwelling or decreases the upwelling of carbon-rich water again to the surface, and therefore actually the likelihood of compound marine heat wave and high acidity events is usually low because the carbon content is relatively low during a marine heat wave in that area. And in the low to mid latitudes, again, the temperature effect wins. And that's why actually we have a relatively high likelihood of those compound events in those regions. Yes, so then when we look into the future, and this has been shown nicely by a paper from Jakob Zeichler, which processes can actually lead to a change in compound event frequency. So it's basically the shift in the mean, which can lead in one variable to a change in the compound event frequency, which is also just a change in the variance without changing the mean, which can lead to a change in compound event frequency. And also then the dependence can change with future climate change between two variables, which can change then the compound event frequency. And we did this analysis to decompose that for marine heat waves and high acidity extremes. And here you see basically the change due to mean variance and the covariability. So everything together. And we see that high acidity extremes, so here shown extreme days per year against global warming. So they basically become almost, so the whole surface ocean actually becomes extreme relatively quickly because of the high signal to noise ratio, because of acidification has relatively small noise versus the signal which is really strong. So every time when we have a heat wave, we also have a compound extreme. That's not really interesting, but it's concerning, but it's not, I would say scientifically not so super interesting. But if we then look at if we get rid of the mean change, so of the distribution, when we only look at the variance change, we see actually quite big change in H plus variability with future global warming. So that's only change in variance and dependence, but we get rid of the mean change. So we use here a large ensemble simulation of the GFDL model, and we actually remove the ensemble mean trend, and then we only look at the variability changes and how that impacts the compound event frequency. And you see that H plus variability strongly increases, and therefore also the compound event frequency actually increases. So why is that? Why is H plus variability strongly increasing, we looked first on which time scales actually the variability changes. So here's the change over basically from 1870 to 2100 in the variance of H plus variations. And here you see that it's mainly the seasonal variability which mostly changes. Not so the daily variability, not really intraannual variability, also not so much. It's mostly the seasonal variability. And then we looked at the drivers. That goes a little bit, I would say, a bit too much into carbon and chemistry now, but the main message here is if you have more carbon in the ocean, the same temperature variation you have from winter to summer leads to a bigger change, a seasonal variation in H plus. So it depends on the background carbon state, how much H plus variability you have due to temperature seasonality. And that actually leads then actually to this big increase in H plus variability. Just one caveat or two, we do not really look at coastal systems here, and we do not really look at diurnal variability, which can also change, but is not well represented in our model we use here. So that leads then to this big increase, the seasonal variations, which leads to this increase in compound event frequency of marine heat wave and high acidity extremes. And the dependence between the variables also slightly decreases, but that change is relatively small and has a large uncertainty. Okay, so I only looked at surface changes so far, but most of the organisms do not live exactly at the surface. They also live probably at subsurface. And if we look at subsurface, and we look at the present day distribution of marine heat wave and high acidity extremes. So at the surface, we had a high likelihood in the mid to low latitudes, but actually at subsurface, at 600 meters, it's totally the opposite. We have a really low likelihood at subsurface in the low to mid latitudes, whereas in the high latitudes, we have a high likelihood. And that's still ongoing work. So Natasha is actually working on that right now. So what she is actually looking at, what are the driving factors of variability at that depth level? And it's mostly the vertical water mass displacement at that depth level, which leads to variations in the different variables. And because the water masses go up and down, it depends then on the vertical gradient of the tracer. So temperature decreases with depth, but H plus not necessarily always decreases with depth. So if then, for example, the thermocline or the vertical water masses goes up and down, that leads then to different changes in the compound event frequency. So here, actually, temperature decreases with depth and H plus actually increases with depth. So if you have a change in the water mass, so if you have a heaving of the water masses, that then leads to actually opposite changes in H plus and temperature, and therefore the likelihood of compound events is relatively low here. That's not the case in the in the equatorial Atlantic, which is actually different. But what is also quite fascinating is if you go to future climate change, and you always expect, compound events get more frequent, which is definitely the case, but there are some regions where actually the ocean is not warming up in the future, at least in that model at 600 meter. And so, especially here in the western part of the subtropical gyre in the Pacific, actually compound event frequency does not increase with future global warming. But overall, so that's my last slide before I wrap up. If we look at the top 2000 meter, and if we look what's the percentage of the volume which is covered either by a univariate extreme in temperature, oxygen, or acidity, or by compound extreme. So today, or in pre-industrial, we have about 20% each day, which is covered by an extreme or compound extreme, and that drastically increases under a fixed pre-industrial baseline. And under 2-degree global warming, about 95% of the top 2000 meters of the ocean will face daily extreme or compound events under 2-degree global warming. And if we get rid of the fixed pre-industrial baseline, if we actually apply a shifting mean baseline, we still have an increase a little bit. Of course, the increase is not as striking as for the fixed pre-industrial baseline, but you still get an increase mainly because the variability in acidity actually increases with future climate change. So to wrap up, yeah, so marine species are increasingly threatened by extreme and compound events. There are conflicting findings at the moment on the impact of marine heat waves on fish, but maybe compound events have a greater effect on those organisms than previously thought. The blob in the eastern equatorial Pacific was definitely a compound event, and compound marine heat wave and ocean acidity extremes occur relatively frequent in the subtropical ocean, but they are rare in the equatorial Pacific and mid to high latitudes. And compound event frequency strongly increases under global warming throughout the water column, but there are some regions actually that may serve as potential refugium for certain species, as in the western part of the subtropical gyres at 600-meter depth, where actually the compound event frequency and overall actually extreme event frequency does not change with future global warming. Yeah, that's it from my side, and I'm happy to take questions if there are any. Thanks.
Thanks so much, Thomas. I'll stop the recording then.